Thanks everyone for joining today. It's a great pleasure to introduce Dan Dorazio, who is an expert on supermassive black hole binaries, accretion disks around them, anything that involves black holes at different scales and gravitational waves. And he's also very interested in observations of supermassive black hole binaries. Dan got his PhD from Columbia, where we were office mates for a very long time. And then he got an Einstein fellowship, and he spent 4 years at Harvard at ITC. And now he's an assistant professor at LNiels Bohr in Copenhagen. Dan, it's a great pleasure to have you here.
Thanks so much. It wasn't that long. We were in graduate school, right? No, okay. But yeah, thanks so much for having me here in Crete. It's already been a great few days catching up with some projects Maria and I have, and also having a few great dinners so far. So yeah, today I'm going to talk all about binary black holes, and specifically the biggest binary black holes at the centers of galaxies, and how the accretion of gas onto these binary black holes is very important for bringing them together, but also making them bright, so we have a chance to find them and then learn something about how they come together, how they sculpt galaxies, and how they create gravitational waves. So we'll be seeing more of these types of pictures throughout the talk. But maybe first, before I leave the title slide, does anyone recognize what that is an image of, or what it is? Probably not, but I figured I'd point it out because it's one of the very few actual observational images I'll show the entire talk. But this fascinated me when it came out. This is an ALMA observation of an accreting stellar binary. So this is an actual image resolved by ALMA of these two protostars accreting gas streamers from a circumbinary disk. And a lot of what I'm talking about today will be simulating this process, not for stars, but for supermassive black hole binaries. All right, so to start, let's take a little bit of step back and understand why this is interesting. I like these types of what you might call gravitational wave spectra, or the gravitational wave sky, an analogy to when you look at the EM spectrum of astronomical observations. Here we have this for gravitational waves, where you have really low frequency, long wavelength gravitational waves generated by early universe type processes, all the way up to very high frequency gravitational waves generated by the mergers of neutron stars or stellar mass black holes. And these are the topic of a lot of fame recently because they've been detected by LIGO in the last, well, 9 years now. Right, so these are high frequency gravitational waves, stellar mass binary black hole mergers. LIGO is detected of order 100 or so now and still looking. But the topic of this entire talk today is if we go to lower frequency gravitational waves. And this, I think, is one of the exciting futures of gravitational wave astrophysics, what is happening here in the low frequency gravitational wave sky. So here, the sources are not the mergers of small black holes, but the mergers of the biggest black holes, right? And we're detecting them and hoping to detect these mergers mainly with these two types of instruments. One, space-borne interferometers, so kind of like LIGO in space, much larger, like LISA, which will detect the mergers of 100,000 to maybe even 100 million solar mass black hole binary mergers. And then also the pulsar timing arrays, which excitingly are now giving us very strong evidence that we might be detecting a background of the biggest 10 to the 9, 10 to the 10 solar mass binary mergers coming together in spiraling before they merge, actually. And so there is, as you might have heard in the last year, evidence of finally perhaps making some detections of these systems in the low frequency gravitational wave sky. And for LISA, this is planned for the 2030s, but finally now the mission has been adopted and will go forward. So this is, I think, an exciting future of this field, gravitational wave astrophysics. Okay, but again, the sources, these supermassive black hole binaries, how are they formed? So it's interesting to note that if you follow any of the science going on with LIGO now, we've detected them, haven't really detected them here, but LIGO has detected them, and one of the main unknown questions is how did they form? What happened in the universe to bring these black holes together? It's not obvious, and that's a very big topic in this field of understanding how did that happen? Well, the same is true here for the supermassive black hole binaries. We haven't detected them, and we're also not 100% sure how they come together. So let me give you an idea of paint the picture of how we do expect two supermassive black holes to get together and merge. Okay, so the picture goes like this. Step one. You have supermassive black holes at the centers of galaxies. We know that. And those galaxies merge. We know that, right? So that's step one. Step three, because we're going to skip a step for now, is that if those two black holes get really close after the galaxy merger, then they'll emit gravitational waves. The gravitational waves carry away energy, angular momentum, and merge the two into something that we hope to detect with LISA, for example. But it's long been unknown what should happen in between step two. So an open question that has been around for 40 years or so is, in between these two steps, essentially what I just said, how does the binary get rid of angular momentum energy to get close enough to start emitting gravitational waves vigorously and merge within the age of the universe, often called the final parsec problem, if you've encountered that before. And so the way that I think about trying to solve this problem is trying to understand how does this binary interact with its environment at these in-between scales. And so the idea is that it can interact with gas there. There can be lots of gas after galaxy mergers that is torqued down to the center to interact with the binary. There's also lots of stars around, nuclear star clusters. Right, the original posing of the final parsec problem was that if you have a spherical nuclear star cluster around the binary, the stars will come in, interact with the binary, steal some energy and momentum, but then you'll get rid of the stars and you haven't taken away enough angular momentum. So what happens? And there are multiple solutions to this problem. So in some ways, it's not a problem. You can figure out how to fix this theoretically. But the issue is still there that we don't know what is happening here. So I want to talk about the kind of program method to try and figure out what is really happening in nature. So as I already alluded to, I'm going to be thinking a lot more about how the gas interacts with the binary. So this talk will be about the gas. The stars can be important too, but there's still a lot to do to understand what is happening in this picture. Because not only does this gas, so this is a numerical simulation of gas falling onto this here eccentric binary, the gas will change the orbital elements of this binary. So it can help drive it to merger, for example. The gas, just like friction on a satellite in the Earth's atmosphere, can help bring the binary together. And we need to understand how that happens specifically so that we can make predictions for the population. What are the merger rates? What kind of binary parameters do we expect to see in mergers with LISA, or do we expect to influence the background of gravitational waves that pulsar timing is seeing? So that's one important reason to look at this problem. The other is that we know that gas falling onto black holes can be extremely bright. And so if we can model how this happens, the hope is that we can find unique signatures of accreting binaries and actually find them somewhere in the universe. And I hope, if there's time, that I can talk a little bit about what I'm doing in each of these directions. All right. I thought it might help to think about all this to first get a sense of scale here with this maybe complicated looking plot, but let me try and describe a little more in detail the kind of the scales available to this binary as it comes together through step 1, 2, 3 that I just mentioned. So what have I plotted here? Here's kind of the orbital period of the binary from, millions of years, a year, down to just hours in here. And the total mass of the binary. So these are typical supermassive masses, 1,000 to 100,000 to 10 to the 10 solar masses. And so up here, we have these observations of so-called dual AGN. That's a picture of one right here where you have imaged two accreting supermassive black holes after a galaxy merger. They're coming together in step 1, and they're separated by tens to thousands of parsecs, these two black holes as they're coming together in the first stage. But as they come closer and closer together, they reach this, what is called the hard binary limit. Essentially, when the two are more bound to each other than they are to all the stars and everything else in the galaxy, or the galaxy center. At this point, you can think of this binary as actually a binary and not just two black holes coming together. And of course, if they get close enough, their event horizons touch here, and they have merged. So this is the whole space of coming together to merging. And I've also put it on here, right, the different separations, and for specific cases, how long it would take for this binary to merge due to gravitational waves only. So this is the age of the universe. You have to get below here to actually merge due to gravitational waves. And I'm going to draw some different regions on this plot and explain what they are. So to think about, when is gas important in this space? When are disks and gas disks important? So I've drawn two little regions here. One says self-gravitating disks. That just means in this shaded region, for a disk to be this large and be surrounding a binary at this separation, it would likely fragment due to gravitational instability. So interesting to keep in mind, you can't keep a gravitationally stable disk around very widely separated binaries. The second one I've called disk decoupling. This just says that as the binary gets very close, it starts to move together very quickly due to gravitational waves, and it moves together more quickly than the gas can keep up. So below these scales, the disk isn't so important because it can't really keep up and influence the binary. So it's really in between here where what I'm going to talk about today is important, which I've just called disk-dominated regime. And you'll see that one, it importantly straddles this line here and can help push it past the final parsec to merger. If that's what it does, we'll see. And then also there's some interesting regimes. You can have these non-gravitating disks, but also possibly fragmenting disks for the more massive systems. So it kind of separates the physics into two regimes here. And if you further put the kind of detector sensitivities of LISA and pulsar timing arrays here, which is just schematic, it's not the full space, you can see that it's these smaller black holes with these kind of gravitationally stable disks that are important for LISA, whereas these bigger fragmenting disks are more important for the pulsar timing arrays and the larger black holes. And I'll plot one more thing on here to allude to a second part of the talk. We get there. And that we don't have any definitive observational evidence of these systems existing in this regime, in this kind of subparsec separation regime. But there are a number of order a few hundred candidate systems that I hope to explain later. And Maria has actually been quite influential in finding many of these. So that's the picture. And I want to now go forward and talk about first what we're thinking about in enhancing these models of how orbital evolution works so we can have better population predictions. And I'll start here. Okay. So, brief primer on gas-assisted orbital evolution for binaries. So this is a plot. I said this idea of the final parsec problem is 40 years old. One of the seminal papers on it is this paper by Begelman, Blanford, and Rees in 1980, where they pointed out that if I have step one here, dynamical friction acting on the binaries works pretty quickly until it doesn't. And then you need something else to bridge this gap, like I was mentioning. And even in 1980, they said, well, maybe gas could do this. And their estimate of how gas could do this is just say the binary has some mass, and mass accretes on it at some rate. And that gives you a timescale for how quickly gas should bring the binary together. And it's fast enough to do it if you make this simple estimate. But the point is, we'd like to have a more detailed calculation of the angular momentum energy exchange between the gas and the binary to understand how this actually happens. And so that's something we've been working on. And how do we do this? So we start with the binary. It has a mass, the larger mass M1, secondary smaller mass M2 is separated with some semi-major axis A. It can have some eccentricity E. We often parameterize the binary masses with a mass ratio. This ratio to the mass is less than 1. And so we want to understand how that evolves, right? Alone it will just sit there at that separation eccentricity forever. So we have to understand how the gas will affect that. And to do that, we solve the equations of hydrodynamics. And most of everything I'm going to talk about today is actually kind of the simplest non-trivial case you can do. Just take a thin two-dimensional disk and solve the equations of mass, energy, angular momentum conservation, assuming a locally isothermal equation of state. And that leaves you with about 4 important parameters: the eccentricity, the mass ratio. You can scale this to any mass or A. So actually, you can take a lot of these results to think about stellar binaries or planets or et cetera. And then there's some parameters that affect what the disk is like, how viscous it is, how thin it is, which affects how important pressure forces are. So a lot of what we're doing is simply this. We're solving these coupled equations for the gravitational field of the binary and the hydrodynamical conservation equations. And then if you want to understand how does the binary orbit evolve due to this gas disk, well, there are two conserved quantities in the two-body problem. It's energy and it's angular momentum, specific energy, specific angular momentum of the binary. And I'm just going to do orbital mechanics 101 here. If you take some derivatives of both sides, you can see that the rate of change of the semi-major axis or the rate of change of the binary eccentricity just depend on its mass accretion rate, L dot, it's the torque on the binary, for example, change in energy. And those are computed, once you know the solution to the hydrodynamical equations, by just summing up what are the forces of the gas on the binary. So very simply, we're just summing up the forces over time that this gas applies to the binary once we have the hydrodynamic solution, and then asking how does that change the orbital elements. Okay, so this is how we're doing the more detailed calculation. And so over the past, actually only 5 years or so, this has been done in a lot more detail, higher resolution, careful numerical calculations of this. And there have been some interesting surprises. In some cases, it's found that the gas doesn't bring the binary together. It does the opposite. So it's not even more up by a factor of a few, it's the sign is wrong, which is kind of startling at first. If you're expecting gas to bring the binaries together and merge, you can't do that if the gas, if the sign is the opposite of what you thought. So this has actually been a debate in this field since around 2017. But I think I won't go into detail on this, but the understanding of how and why this happens is, I think we've converged on this now. And more than that, I helped to lead a code comparison project recently where we took everyone working on this field in about 10 different numerical codes, and we brought them together and asked, do we all agree on this? And so this paper, this code comparison paper, is just out on the archive a month or two ago. And what's nice is across codes of different numerical algorithms, and different approaches, we've been able to find some convergence on this result that the binary does indeed, its semi-major axis is increased by the gas, but only in certain parts of parameter space. So it's not the end of the story. It's not that when you grab gas, you're going to rip apart binaries. That's not always the answer. And also when that does happen, you only bring them so far apart and other things will take over. So it's not saying that you can't bring binaries together, but it is a surprising result and made us realize that we need to look more carefully at how the binary responds in many different situations. So just to give you an overview, we've been finding also now that there's a non-trivial dependence on the binary and the disk parameters. You'll get different results depending on, for example, the binary mass ratio. What I showed you was, this is for more equal masses. If you have disparate mass binary systems, they will come together again. And again, I'm just going to gloss over this and give you the punchline of a few of these studies. If you make the disk thinner, it's also more likely that the disk wants to push the binary together. So pressure forces are less important. If you change, again, the viscosity in the disk or the disk thermodynamics, you get a wide range of results, which at the end of the day will need to be understood because binaries will go through many of these different scenarios. They're not just sitting in one type of disk. And I can talk more about that later if you're interested. But I wanted to dig into one result that I find really interesting and we put together not so long ago now. The one thing I didn't mention is the binary eccentricity. So that is an important thing we expect to arise in the universe. And so we started asking, how does the binary eccentricity respond in all of this? Whether or not the semi-major axis is coming together is one thing, but what's happening to the eccentricity too at the same time. And so to do this, we carried out a kind of a numerical experiment, I'll call it. And the idea is, again, we're measuring these rates, E dot and A dot and a few others. And the experiment we do is we put the binary here on a fixed orbit. And we very, very, very slowly increase the eccentricity of the binary orbit by hand. And when you do that, you can measure at each eccentricity, what are the forces on the binary and how does it want to evolve? And when you do that, you can put together kind of a phase space portrait for how it should evolve in time, and you much more efficiently get this idea of what it's going to do. So we did that. Let me first show you a picture, a kind of movie of how the disk responds as the eccentricity changes, because sometimes that's what you do first anyway. You solve all these equations and you just look at pictures first. So let's look at this. This is density of our disk. So this is high density, and here's this really low density cavity that, as you might have seen by now, the binary, because it's like a propeller in the disk, clears this cavity around it. And so what I'm going to do is show you strobes, snapshots of the binary at pericenter for higher and higher eccentricity. So this is circular here, and that green line is the mutual orbits of the two. So I'm going to look at snapshots here as it gets more and more centric at pericenter. And you can try and look at if there's something obvious that's changing. I mean, just try and get an idea here of what's happening as it's getting more and more centric. Because there's one interesting thing to look for, and I can explain what this is in a minute. But the interesting thing is that, let's stop it here actually. At relatively low eccentricities, you get this really kind of, I would call it a lopsided disk. It's not symmetric around the binary. It grows into this state where it's actually, the disk itself is eccentric. And that eccentric disk precesses very slowly around the binary. And that's what I'm measuring here, the precession rate of that disk. So for low eccentricities, it's eccentric and precessing at some rate, 200 orbital binary orbits until it goes all the way around. But now, as the eccentricity grows, okay, this is just what it looks like on orbital times. But as the eccentricity grows of the binary, you'll notice it pops into a very different looking state at medium eccentricities. So here's at like 0.3 or something, E0.3. So this kind of asymmetric state really quickly goes away, and you're left with this symmetric state, which doesn't precess. It's kind of locked to the binary eccentricity, okay? But then it transitions again as you go to higher eccentricities. This is what's going on here. It's much more like m=2 symmetric. But as you go to higher eccentricity, it shoots again into this asymmetric state at higher eccentricities. So we thought this was pretty peculiar because there's really sharp transitions of where this happens. Something must be going on. We can understand why is this happening. But without even saying that, now what I can show you is, okay, so this is what the solution to the hydro equations looks like, just the disk morphology. But these transitions, it turns out, maybe it's not surprising, are really correspond to drastic changes in the expected orbital evolution. And so I'm going to show you another first seemingly a lot going on plot. But here is this resulting, what you might call phase space portrait of the binary evolution. So I'm plotting A dot, change in the binary semi-major axis, and E dot, change in the binary eccentricity. And I'm plotting them as a function of the binary eccentricity, because this is really, for a fixed mass ratio, this is the only important orbital parameter in the problem. And so this purple is A dot, and here's 0, right? So this purple line above 0 means that the binary wants to expand, like I said before. 0 eccentricity, this is what people were finding. The binary wants to expand. But then, of course, if this purple line is below 0, it's being driven together. So you can first see that there are some changes in eccentricity in A dot. And then the orange line is E dot. So here, when E dot is below 0, it wants to circularize. So it wants to move this way in the diagram. So anything starting here below an eccentricity of 0.1 wants to circularize. But actually everything up here is driven, it pumped to higher and higher eccentricity. And then up here, it wants to circularize again. So you can put this together and you realize that there are actually 2 fixed points in this evolution. It becomes a lot simpler than this whole diagram. That depending on where you start, and ready for all the Easter colors, wait, I'm going to put those up there first. These are the different states we just talked about correspondingly on this diagram. You can see there are 2 attracting solutions. One at 0 eccentricity, because anything that starts up here will become circular, and it'll want to expand. But anything that starts here is driven to this point. Everything that starts here is driven to the same point. So there's actually an equilibrium solution, equilibrium eccentricity at strangely around an eccentricity of 0.4. And it seems to be completely tied to where I showed you those transitions in the disk state are here, specifically from the symmetric to anti-symmetric asymmetric state. And so after all that explanation, you're left with these eccentric equal mass ratio binaries. You have two solutions, a circular out spiral, but also, interestingly, there's eccentric in spiral. So you'll have these binaries stuck at an eccentricity of 0.4, and they'll slowly in spiral out that eccentricity until something else like gravitational waves take over. All right. So, and actually, how much time am I at already? We're good. So yeah, I wanted to explain. So this new picture we're putting together for these expanding the parameter space for understanding orbital evolution. But I wanted to show quickly, and I'll just give the summary right here, just what I essentially just said, that this is very different than the usual picture. And it's nice on the hydrodynamic side. We're trying to understand what causes these state changes, because if we can do that, we can get a better understanding of how this might occur in the wider parameter space on the physics side of this problem. But what we can also do, and it's the last thing I'll say about orbital evolution quickly, is recently I realized that that whole problem in that machinery we built, you can just put a minus sign in your code and you get a retrograde disk. So we reran this whole calculation essentially for a retrograde binary. The reason being that these are astrophysically important too. The retrograde circumbinary disk is a stable solution, meaning that if you say you create the disk by some cloud with random angular momentum coming in, if it's closer to retrograde, it'll align retrograde. If it's closer to prograde, it'll align prograde. So this is another reasonable state you might expect the system to be in. And then here, we don't need to go into this too much, but there's some interesting physics of resonance that disappear when you flip the disk, so you can help you understand what's happening with these transitions that I talked about. But okay, so what we did was a new study across the whole domain of eccentricity, and also one of the first very high resolution studies that looked at everything that's going on in here. And you'll notice this is actually super boring. This is a circular retrograde binary. It doesn't look nearly as interested as the prograde case, because you do get rid of all these resonances in the problem. But what happens when you increase the eccentricities, you get quite an interesting parameter space to move through. And if you're curious, I can tell you more about the physics going on here. But the punchline that I want to get to is that in this case, with the retrograde binary, the results for the orbital evolution are quite different and actually quite simple. It always decays. The binary always pushed together, and maybe a few to even 10 times faster than in the prograde case. So just a figure of merit, there's an exponential decay, so an e-folding change in the separation after only 1/10 of the mass doubling time. So saltpeter time, you can bring this thing almost together. And then there's always a fast eccentricity pumping. It wants to drive it to high eccentricities, and it does that also very quickly. And so you could ask, if you're bringing this together quickly and making it very eccentric, at some point gravitational waves take over, which means gravitational waves want to circularize the binary. The disk wants to do the opposite. There's some equilibrium eccentricity where you'll match. And if you just estimate what that is, without going into too much detail, here's another one of these diagrams with binary orbital period and mass. And what we plotted out here, which are hard to see, are what is this equilibrium or maximum eccentricity? Sorry, maximum eccentricity. And I'll only point out that there are lots and lots of 9s here. So you can really pump eccentricity a lot here. And I'll say one more thing about that. But first, another observation here. So drives eccentricity, brings it there quickly. It also generates these little disks here, which I call mini disks around the two black holes. They also form retrograde to the binary angular momentum. And that means they want to spin the black holes up in the opposite direction of the orbit. And so if you've encountered one of the main things you can, for example, LIGO measures when it measures a binary in spiral, is something called chi effective, which tells you which way that the spins are pointing relative to the binary orbit. This would mean that you should create maximally negative chi effective, which is something kind of strange to see. And it's strange to see if it's also correlated with eccentricity. So we recently did an analysis of what you might expect in the Lisa band if retrograde disks are driving these binaries to merger. And you find that they should be have an eccentricity that's detectable and have these retrograde spins. So it's actually kind of an interesting observable that we'll have to keep modeling in more detail, but it could be something that when you see these mergers in LISA, you could say, well, that could be from this channel. So it's a kind of interesting result that came of just looking at this retrograde problem. All right. So let me take a small break there, because that whole first part was just about kind of some vignettes and what's going on and trying to understand orbital evolution for these systems. But I think I can sum it up in saying that, right, we need to do this to understand our predictions for supermassive black hole mergers better. They're wildly uncertain still. But we're finding that there's an extremely rich and complex response to the binary depending on many things, and there's still a lot more physics to add. I noted these are all isothermal, so there's a lot more actually that will happen in this picture, and that's what we continue to work on here. I don't know if people want to interrupt me at any point, that's fine, but I think I'll go on to part 2 when we're ready. So, talked about this. Now, using the same kind of calculations, just want to ask, is there anything interesting we might expect electromagnetically from this accretion onto the binary that can help us look for these systems, make some discoveries of close separation supermassives? So here we go. And let me first point out, like I already said, that we don't have any definitive evidence for subparsec separation, supermassive black hole binaries. There's lots of candidates, as I mentioned, but we're still looking. And so I want to then ask the question, how do we look? Is there hope in finding any of them? Because, right, this is, I mean, I think people have been looking for these for 40 years, right? So maybe I should try and tell you why there's some hope to keep looking. Let's go back to one of these plots again. I think of this part of it, so the searching for these systems is trying to get to the point of doing demography, right? I mean, making predictions for what the population should look like. It doesn't really mean a whole lot until you can have a population to compare it to. So I think it's really necessary that we have to do both of these at the same time. Because at some point, it'd be great if we had, candidates throughout here, and based on the density of how they fill the space, you get an idea of what's pushing them through the space, right? That's the idea. And so recently, Maria and I wrote this review on all the different ways that we know of at the moment to look for these systems. And here's a sampling of them as they fill the space. So I won't go through all of them in turn, but of course there's gravitational waves. LISA's getting these mergers of the smaller binaries. Also, timing arrays are getting the inspirals before merger of the biggest supermassive black hole binaries. And then you can look at, for example, these are a number of different electromagnetic methods, mostly indirect methods to infer the existence of a binary. Are there wiggly jets that could be there from the binary's orbital motion? Are there emission lines that are moving back and forth due to Keplerian motion of a binary? This one I won't talk about, but I'm thinking about this one a lot, is can you actually find direct evidence and resolve them? Because the EHT, for example, has the resolution required to, let's put it this way, the Milky Way black hole, which EHT is looking at, has the same angular resolution in the sky as a supermassive black hole binary at a gigaparsec, separated by like, 1/100th of a parsec. So they're the same relative scales. And these have orbital periods, which are 10 years. So it's something that you get really lucky. Maybe we could one day actually look at one of these. But what I'm going to focus on is this idea of looking for periodicity in quasar light curves. So what is this picture all about? And that's really what most of these candidate systems are from, this method that I'm going to talk about. These are actually jets, wiggly jets that people have thought maybe are from binary. But let's look at what is this periodicity method. I think the easiest way to explain it, actually most of those methods, is to look at, we expect these to be at center of galaxies. Active galactic nuclei are really bright centers of galaxies, and they're driven by accretion onto a black hole. So I think it's just a creative game of saying, now what does it look like if I put a binary black hole here? And this method says that if you have a binary black hole accreting, as I showed you in the simulations, is churning up the gas. And is it possible that the binary's orbital period imprints on the emission from this quasar, so that if you look at some quasars, they might have some periodic oscillations in them. That's the basic picture to all of it. What I want to talk about is what actually causes this oscillation. So how can accreting supermassive black hole binaries create detectable periodic variability in quasar-like curves? Is this unique to black hole binaries, and can it encode somehow the system parameters so we can learn more about it? And so to answer these questions, I just want to go through some ideas of how you do create periodic variability from kind of a theoretical modeling point of view. The first one is maybe obvious. The accretion rate can vary. If again, you do one of these simulations, you're accreting onto the binary, you measure the rate at which gas falls onto the black holes, and that tracks how bright the emission from them will be. You look at this and you find, well, first two main things. One, the accretion rate, maybe not obvious at first, actually can match that of a single black hole. This propeller motion doesn't keep the gas from coming in. It still comes in and accretes at a high rate, so it can be as bright as the normal model for quasars AGN, but then it's also modulated very strongly. And the way that it's modulated, here you can see it's mostly at the orbital period, depends very much on the binary parameters. And so I won't focus on this dependence, but I can give you a flavor of it. If you change the binary mass ratio, that's Q. So very small Q means here we're looking in the frame of the binary, this much smaller black hole orbiting this much bigger black hole. You mostly find the accretion steady. It doesn't perturb the disk all that much. But if you increase this mass ratio above this kind of magic number, somewhere around there, now also in the rotating frame of the binary, you see that this cavity that it clears starts sloshing around at the orbital period. So you start getting orbital period variations. And then if you go to near equal mass, up to Q.5, Q of 1, equal mass ratio, then you get this asymmetric, much more nonlinear complex picture that we looked at earlier. And here you start getting an interesting ratio of periodic variability due to what's happening out here in this disk and also what's happening in here. And so we've looked in detail at kind of periodograms across the binary parameter space of what periodicities show up when. And this is something we continue to study more as we add more physics to these simulations. And of course, as you change the eccentricity, you also get a rich structure variability in the accretion rates of these systems. Oh yeah, we're not going to look at this. This is this rich structure variability I mentioned, and this is something we're looking at. But the main idea is that, yeah, you change the binary parameters and you get different periodicity timescales, usually tied to the orbital period, though. Okay. But I said that at small mass ratios, it's pretty steady, right? This is, again, the simulation in the rotating frame. It's the accretion rate's just kind of stochastic steady. And then even sometimes when you do have accretion variability, that variability can be buffered when it's translated into actual flux luminosity due to different timescales in the problem. What's interesting is that even when you don't have accretion rate variability, you expect relatively robustly that relativistic effects can still prevail. And those, due to the orbital motion of the binary, can create variability via the relativistic Doppler boost, just from the orbital velocity, which I'll go over, and also gravitational lensing. So those will act all the time, and I like these ideas because, right, relativity happens. These should be there at some level, as long as it's accreting. So let me give you a quicker, more detailed idea of what I mean. Here's us looking at our binary, inclined to the line of sight. Imagine the smaller one's accreting. This is like our light bulb, and it's orbiting. Here's another view. The smaller one giving off light is orbiting. You know, the relativistic boost just says that when it's moving towards us, it looks brighter. When it's moving away, it looks dimmer. I'll say something more about that, but that's the basic idea. So circular orbit, you just get this sinusoidal variability given by relatively V over C of the orbit. So be few to 10% amplitude. Okay, but now you have even closer, your binary is even closer to the line of sight. You get the Doppler boost, the sinusoid, but also when this little one, our light bulb, passes behind the big one, you get a symmetric lensing flare. And so this is actually quite unique looking light curve. You have a symmetric flare on top of a sinusoid, but specifically, these are phase matched, so this flare must always be right here. It has to be when this one goes behind that one. And also, what you can show is that this is not so improbable to have this alignment. At the separations we care about, where the orbital periods are years, this is actually, could be a 10% of systems. So, so these are really interesting because they can be kind of unique, and they should happen. And even more than that, I want to just go over, there's some multi-wavelength predictions here too. So lensing flares are achromatic most of the time, as long as that's a point source. So this flare, if you saw it, should pretty much be the same in all wavelengths, but this sinusoidal feature shouldn't be. And here's why. Here's another picture of how the Doppler boost would work. Here's us looking at our binary, all the lights coming from this guy. We look at it with our telescope, we get a spectrum, and just approximate that with a power law, and say we're looking in the V band. So the total flux we see at one point in time is just the integrated flux under here. And let's make a point on our photometric light curve at this point in time. Okay, the orbit moves on. The secondary emitting light starts moving towards us. Of course, beaming makes it look brighter no matter what, but it's also blue shifted. And when you blue shift a spectrum with this slope, the amount that it gets brighter is dependent on that slope, right? Same thing as you go back the other way. So what that means is you can predict the amplitude of this modulation dependent on the orbital velocity, which you can get from the period and an estimate of the mass, but also the measurement of the spectral slope. And that becomes powerful because if you can do this in multiple observing bands, for example, optical and UV, and you can measure slopes in those bands, then you have a parameterless prediction of how the oscillation should look at different wavelengths. So that provides you a pretty good handle. If you can get UV and optical spectra and time domain data, then you have a pretty good test of this picture. And of course, Maria has probably maybe told you about this before. There is a quasar candidate that we've been looking at now for 9 years, which exhibits some of these properties. But finally, there's more data, and we need to understand if this trend is happening. It's continuing to happen, right? Because this is very hard to see, but this black line is the fit to the optical data in gray. And then when we first looked at this system, it did have UV and optical spectra, and so we measured the spectral slopes in each and predicted how the optical and the UV should be relative to each other. And at first, it seems to have matched archival UV data based on the optical, but this system is still being looked at, and hopefully soon we have the definitive test of this hypothesis for this quasar, PG 1302. Okay, that's the Doppler boost and how I think it can be a pretty useful tool going forward to try and understand if variability is unique to something like a binary, a supermassive black hole binary. But even perhaps more powerful if it comes around is this lensing idea. So here's real data of a system looked at with the Kepler mission, looking for planets, right, exoplanets. And this was a system that I gave a talk on lensing a while ago, and somebody showed me, look, I found this in an AGN in the Kepler field, and it looks a lot like if you make those same self-lensing plots I just did, but make the binary eccentric, you can get things that look like this. So what we did was just fit these relatively simple lensing plus Doppler boost models to this data, this AGN, which is named Spiky, not by me, but maybe you can get why. And what we found is that you can, and if you zoom on this flare too, it's actually quite interesting. It has some structure here, but it's relatively symmetric when you take out the trend, the rising trend. But we could actually pretty well fit these lensing models to this data, and they fit this flare quite well. So this, of course, isn't repeating, right? There's only one, but we figured it'd be quite interesting to say one of the powerful pieces of this model is that if you can fit this flare isn't totally, you can't really massage it. The magnification and the width are set by the orbital parameters, by the orbital period. And so once you fit this, you know the orbital period has to be something within some error. So we predicted if this is really a binary and this is really self-lensing happening in that binary, then this flare we can predict when it will happen again. And I wish I could give you the result, because this is a few years ago, but we did predict, did get some, gather some data on this system. Actually, we didn't learn about it until out here, so the uncertainty is a little larger. But we currently do have a combination of LCO, ZTF, Gaia, Atlas data on this, and we're hopefully finishing with Maria as well. Long-awaited paper on if I can tell you if this is a binary system or not. But I can give you the punchline is that we did monitor this. It turns out it's very hard to find a few percent 10-day flare in ground-based data. So I think the conclusion is inconclusive, although we found some interesting results where we do still seem to find this kind of oscillation. So I think it's an interesting system to keep watching, but we haven't been able to say for sure, because we don't have Kepler anymore, if this happens again. So, but what's actually, and I'll get to it in the end, this isn't really, hopefully there's more of these systems with LSST and Roman, which I'll mention at the end, but I think it's a promising method. Okay, I wanted to finish here with just 2 or 3 additions to this idea of hydrodynamic variability, Doppler lensing variability. Of course, they can both be happening. And recently put out a paper where we studied this, essentially coming up with emission models for this disk and adding on the Doppler boost and the lensing to the hydrodynamic variability. And all I'm going to say is that for different inclinations and binary parameters, you can get a whole zoo of different light curves. And what we're hoping is that these will be useful in doing searches for these systems, because you can get some really bizarre things, these double peak structures, these huge flares. And what we did was put together a code that will allow you to create these light curves for people that are interested in making mock data, mock signals, for example. Okay, and then a final point. Talked about the direct variability in the emission from the accreting binary, but there's all this other stuff around, right? There's a dust torus, broadline regions, blah, 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 blah. All that periodic emission can also interact with that. And we've thought a little bit, we'd like to think more about how this kind of what I call reverberated emission could also give you a handle on asking whether this is a binary system or not. So I just want to mention this at the end, is that we thought one about this dust torus. Here's that binary. We get some direct, say, optical variable emission from it, but it has a whole other world around it besides us. There's this dust torus here. That emission will also periodically heat up the dust. And then in the infrared, with something like WISE, you might see also at the same period infrared variability, but specifically there will be a time lag because of this light travel time, and there'll be a diminishment in the amplitude, also because there's a finite light travel time across that whole surface that it's reverberating from. And this is data actually for that same quasar I just showed you. It does have this. You would expect this for any oscillation in optical, there'll be an oscillation in the infrared. But what we tried to do is ask, could that be specifically from the Doppler boost? So we built reverberation models. One, when you illuminate the dust like this, like a lighthouse, Doppler boosted lighthouse, and one when you have isotropic variability, and we asked, can you tell the difference? The answer with this system was no. It was consistent with both of them, but maybe more data will tell us. But I think also this is an interesting something to keep in mind going forward. If we can get, of course, IR time domain observations at the right cadence, then you can test some of these models. You might also find these orphan kind of variability in the IR, right? If the binary is like, say, face onto you, you don't see any Doppler variability, you don't see any lensing, but the dust around here does. So maybe there's a way to look for these systems in the IR. Last point. Same model, we have this Doppler boost variation. We see that directly, but if there's gas around it, maybe even the circumbinary disk itself, that light will scatter from the gas, some of it will come to us and will be polarized. So one possible thing to look for too is maybe polarization signatures. And so we also put together a simple model where if you see this direct emission oscillation from the, say, the Doppler boost, or just an isotropically pulsating emission, and you ask, what does the polarization fraction look like over time? What does the polarization angle look like over time? And I think the punchline is the polarization fraction is actually quite small, 0.2% or something here. But it does have a relatively unique signal compared to just the isotropically pulsing source, which is orange. It has this variation which peaks at the minimum of the direct flux at the same period. If you can resolve this type of change in polarization, which I don't know, maybe people here could tell me that seems small, but interesting. The other thing, if you can measure the polarization angle, it varies at twice the period of this due to the relative symmetry of this system. If you had a less symmetric system, it might be a little more close to this period. But yeah, another handle on these systems. Okay. And then finally, I gave you a few different candidate systems and different ways to look for these things. But we've also looked at the populations, expected populations based on our predictions, and asked, in the future, are we going to find any more of these candidates? And I think the future looks bright based on these calculations where we've taken big populations from cosmological simulations of binaries, painted on binary evolution, and asked, in this study, how many could we detect lensing flares from with LSST? And the upshot is, given some fiducial parameters, the number is tens to hundreds. So if we could actually access a population of that size, then we can start learning something with LSST. But I know something Maria's working on. How do we find these systems in LSST is a next big challenge as well. Also, the Roman telescope will be a much more narrower field of view. This will launch in 2027, but it'll have them, single visit 28th magnitude in the near IR. And so you'd be able to see much smaller systems, much smaller mass systems. So you probe a different, essentially, set of black holes that will be right before the Lisa band. And so in this white paper you can check out, we estimated that Roman could maybe even find a border 1,000 of these systems at small periods right before the Lisa band from periodicity. Okay, so that's the point. I think there's a lot of work to do to understand accretion so that we can look for these systems and better model their population. And this is essentially what I'm saying here. We need to understand the signal better, what I just showed you, but also, as I know people work on here, the noise better. If you're going to pull a signal, you're going to find periodicity in quasars, you understand what noise you're drawing it from. That's a big part of this that I didn't talk about, which also needs a lot of work. Right, we need to find work on the right algorithms to pull this data out and link it to these theoretical models. And in the future, also constrain with multi-messenger observations. The pulsar timing arrays tells us there's a certain population given the background. We can use that to constrain the candidates, and that has been done. And yeah, I think I'm going to leave it at that because I threw a lot of things out all at once, but I think it's a pretty interesting field going forward. And I'll just say, since I'm in Crete, that much like this accretion disk, there are still many mysteries in accretion disks. Which I hope to go see tomorrow at the Archaeological Museum.
Yeah, maybe it's not just one question. So okay, and if you go to part one, I guess what you showed is like sort of how the binary responds to, okay, so first question. So if you increase the eccentricity, you also make the gravitational wave emission more effective with longer separations.
Yeah.
So is this somehow taken into account in this? Are this like GR hydro simulations or?
No, it's a good question. What we did here was try and model earlier in the evolution where the GR is quite weak still. So we measured just the gas torques. But then when we do an actual model of the population, we add the gravitational wave emission to it. So we have two separate terms, essentially. There's a gas torque term and a gravitational wave term, and one will dominate in one regime and one will in the other. So that's actually what leads to, I mentioned that in this retrograde scenario, you could get very high eccentricities. At some point, that stops.
If the eccentricity is close to one, then it's also important. Even.
Yeah. Right, eccentricity grows, and then at some point, gravitational waves just don't allow that to happen anymore. And that's what we modeled in this paper that you can't really see. The title up here, we actually put those two terms together, and then you get eccentricities you would expect in LISA, which are like 0.01, 0.1. The gravitational waves bring them down to much smaller by the time the merger starts.
Okay. And then I guess what you showed in this part one is how the binary wants to evolve for like a fixed eccentricity. But can you say something about, I mean, there should be some eccentricity popping due to the interaction with the superbinaries.
Yes.
Do you expect some of that to like leave an imprint on the gravitational wave background? But sure, I mean, this eccentricity should not go away.
I mean, that's a good question, how that might affect the gravitational wave background. So yeah, so this is saying, this gives you the whole evolution of a binary actually, as long as the mass is not the mass of the disk isn't very high.
Right.
Yeah, right. So this is saying that you start here, this would be the gas term, you'd also want to add a gravitational wave term. But as long as the gas is dominant, the binary would just evolve to this point. And so it will sit at this 0.4 until it gets closer where gravitational waves dominate. And then at that point, gravitational waves will take over and try and circularize the binary. And so I think for this scenario, this 0.4 isn't really high enough to give it as large eccentricity near merger. But in the retrograde case, it might be high enough. And we haven't looked at if that would actually affect the turnover in the gravitational wave background.
I mean, even for the PTA like separations, so that even at that point, the eccentricity will expect the eccentricity to go away.
Yeah, I don't know if it will affect the turnover or not. I mean, the tricky thing with the pulsar timing array binaries is that they might be surrounded by this gravitationally unstable disk. And so it might not be completely applicable. But if you say it's applicable, I just assume that for now, and it still works this way, then it could cause, yeah, maybe at the very low frequencies, a little bit of loss of power due to eccentricity. I mean, it's a good point, right? Because if they're eccentric, you have this turnover at the low frequencies. Yeah, but I mean, I think it's an interesting point.
Yeah, thanks. We should read more about this.
Yeah.
And I have a question about time scales. So in the last part of the presentation, the observation part, the time scales of the variability are of the order of a few years, and this is because of the orbital period of the two black holes. I understand, right?
Yes.
Okay. Now, when you discuss the changes in the end dot because of the accretion bits, what are the time scales of this change?
Those can be, so usually that's many thousands to tens of thousands of orbits, if I understand the question. Yeah. So an M over M dot, essentially, that's, I think, tens of thousands. It can be more or less, but many orbits.
Right.
Yes.
So.
Oh, wait, sorry. Which M dot do you mean? Sorry, maybe we're talking about two different things. There's, just to be clear, there is kind of an M dot on the really short time scale that's doing this.
I'm talking about the end of when you have the binary black hole, because of the changing structure of the accretion disk, you change the end dot on each one of the two black holes, and then you present it a multiplied curve of the variability that you would expect because of this change in end dot.
Oh, yes. Okay, so those changes are on the orbital time scale.
Okay.
But when you average over an orbital time scale, then you just have a very pretty much steady accretion rate. So yeah, these changes back and forth are on the orbital time scale.
A longer time scale because, okay, if you go.
Yeah. Is it maybe here that's worth looking at, or?
Exactly.
Okay, yeah, we can look at the green thing. Oh. Yeah. Yeah, this is real time with that simulation. They're matched.
So what is the time scale of that?
Yeah, so this is 10 orbital periods, this whole thing, and the orbital period is up to you to choose in this problem because it's scale free. Yeah.
So because what I was wondering is, what you're observing is a combination of the two effects. Is both the change of the end dot, but also the Doppler boosting and the relativistic effects and so on.
Yeah.
And the Lensing effects and so on. So if you have large variations of the end dot, you may change the structure of the accretion disk right around the black hole, which means that you change the observational signature of the accretion disk. You may have like disappearing emission lines. So you may end up with changing loop ATM, for example.
That's a very good point. Yeah. Yeah. So yeah, if you have emission lines, for example, coming from these regions, then they're really being freaking up.
That's one thing, but also if the variations of the end dot are too large, you go from a negative accretion disk to the 10 to the minus 3 subelectron or 10 to the minus 4 subelectron. Then you may move from a broad line AGN to a narrow line AGN, or even a liner type AGN where you don't have strong emission lines.
Okay, so I've been actually very much working on now, if you change that accretion rate a lot, like you said, you could go from, I would say, like a thin disk black body disk to an ADAF.
Right,
exactly. Yeah, it's something we're really interested in looking at because I'll give you an example. We calculated, you can calculate this MW. You can also calculate how much does this one get versus this one.
Right.
And so if you split the accretion from far away, often the secondary takes much more, which starves the primary. So you could have one of each, and that could be.
So the question is if you can make predictions about the population of these changing loop AGN, because this is something that with future spectroscopic surveys, that's something that can be measured to be quantified.
Yeah, so changing look, is that usually like decades, or I guess it's a whole range of time?
Yeah, but this is because of the rate of the observation. But if we have high cadence in spectroscopic observations, then possibly one system is like that.
Or it could be the longer period binaries are more common. So we're talking, yeah, that'd be very interesting to look at it if there's a relevant time scale too to compare to the orbital period in this case. So something turning up drunk. I like that idea.
Thanks for the great talk. So as someone whose favorite observation tool is VLBI, which is something you mentioned briefly, but you didn't have time to go into. So is your, because I think even with something like the EHT, you wouldn't be able to resolve a binary system and include both accretion disks, but is your plan sort of to look for the astrometric signatures? If you just have, say, a binary with like one companion is like significantly more massive than the other, then you would like see an astrometric shift and with some kind of periodicity.
Yeah, that's the idea that you could get an like a center of light kind of motion. Because with spectrometry, then you can get to like 10 or less microarcseconds or kind of resolution. Yeah, that's exactly the idea. But one difficult thing is for a single black hole, you can come up with a reasonable model of what the shadow on the disk looks like. Here we're a little far away from asking what does that system look like, given that you might have a very messy center. Then there might not be 2 point sources, right? Yeah, there are 2 point sources. That's exactly, I think, what we could do. Once you find a candidate that's radio loud, follow it up with some VLBI measurements in different phase lines over a long time and see if you get that shift.
That would be very interesting to do. Although, observationally speaking, we're still like exploring this the possibility to observe this at high frequencies, because astrometry is still impossible at these high frequencies. People are working on this. I'm also working on this because your atmosphere is very volatile and makes your astrometric accuracy very low. But so
that's the millimeter or sub-millimeter.
Yes, it's technically it becomes possible these days in the coming years to do astrometry at very high frequencies, millimeter wavelengths.
Well, I should ask you some questions later. Let's see. Yeah, about how to do it. Thanks.
Right. Thanks for the very good talk. I'm wondering, this is hydro.
This is
pure
hydro.
hydro.
Yeah, this is hydro. Yeah.
There is no radiative transfer.
No, yeah, as I mentioned, it's, no problem saying this is the simplest non-trivial case. It's really stripped down, yeah.
And just to make the comment that, well, one of the largest paradigm shifts in cosmological simulations in the last decade was feedback.
Yes, okay, yeah,
And that changes how all these disks and gas around the supermassive black hole evolve.
yeah.
Time, right? Because you have a lot of the amount of energy released in these accretion events,
Yeah,
and you put a lot of momentum into the gas. So it would be, I mean,
yeah,
the next step. No?
I completely agree. I think I either get that point or MHD. And I think that actually the radiation pressure is going to be more important first,
Radiation.
for sure. Radiation is radiation. Yeah, I completely agree. Also, for spectra, if you want to understand what the emission looks like, this is optically thin, this is optically thick, and then there's a lot of interesting things, I think. So I agree.
Impressive thought.
I can talk later today too.
Questions. Let's thank Dan again.
Thank you.